heard we're in week 9. Week 9. And just wait 2 months of Christmas break. That is absolutely crazy. It's gonna feel so different. Sometimes you have like Thanksgiving, and I don't know. I'm sure you guys feel the same way. You get done Thanksgiving meal, and it's like a 4-day weekend or 5-day weekend, and then like Friday or Saturday hits, and you start thinking, "Oh crap, I've got finals coming up." That's not gonna happen this year. It's not gonna happen this year. All right, exam. It's live today. You should be able to see it, right? Right? On Blackboard. All right. So there is a time limit for part 1. I think I told you how many questions there are. 28, maybe. All right. So you can like keep track. I don't know if it tells you like question 1, question 2, or whatever. If it increments the number, I don't know how that works. But know that there's 28 questions. The R marked down is, I think, 41 points total. All right, so the points for each question are marked. I didn't do for like all the points for like A, B, C. It's just like question 1, this is how many points it's worth. And I think you could probably figure out some of the distribution. I mean, depending on what you have to do to answer the question. But we'll add the points together, so it comes out to be 69 points total for exam 2, which is lower than what we normally have. That's also because for our theoretical in-class exam, I would have had you doing some of these, the normal curves and so forth, and doing some of the binomial and Poisson distribution by hand. So we've got fewer points. You have to complete that part 1, or you have to start that part 1, the exam part, I think by 11:30. By 11 or 11:30, and then the R stuff has to be uploaded by 11:30 at night tonight. For lab, I'll be in here. So if you finished up the markdown and you want to try to get it uploaded at that time, if you run into problems, I'll be here during our lab time. Might be a little bit late getting back here, but I'll be here up until 4. All right, so you can feel free to come in here and do the exam at that time. All right. Any questions? Homework keys were posted, all except that optional homework. The homework keys were posted, so you can check those out. It was on one of them. You'll see that I did the probabilities by hand, and then on another page I actually have the R script. It's not set up as an R markdown. It's just the scripts that answers the problem. All right. If you don't have questions, we'll continue. So I should have looked at this earlier. I had kind of revised some of the presentations, even the ones that we've already done last year, and didn't really even consider it. But this was one, and we already started to kind of cover it. Definitions, null hypothesis, alternate hypothesis, test statistic, null distribution. And I believe what I've done, I think I did this on Friday, is I opened it, made the PDFs again, and then uploaded the PDF of the presentations into Blackboard. So if you already downloaded it and are following along, you may see some slight changes. Some of it is just spelling corrections. I added some new stuff. So this is one, because we kind of went through the whole idea of p-value, and what we're doing is getting this area under the curve, because a p-value, if you remember the definition, and you do need to know the definition, it's a probability of getting data as extreme or more extreme by chance alone if our null hypothesis is true. So we're looking at possibility of being equal to what we observed or more extreme. All right? For a discrete distribution, we calculate those values directly. That is a exact probability. All right? But other times, we have to use approximations, and in this case, this was a t-test. That approximation, our test statistic, ends up following a t-distribution, which is continuous. So we can't calculate the probability at each value because a continuous distribution, those probabilities are like super, super small. So what we have to do is do the area under the curves. All right? And then we get to this idea where we have our test. All right? So I think this is one that was definitely revised. Gives us a much better idea of the acceptance region, rejection regions, and for this example, I give you our p-value area. So what our regions are is we're looking at 95% of the values. All right, 95% regions, a confidence interval. In that interval, we say it's possible just by chance alone that we'll get values in that region. And for that, I call it the acceptance region. All of the area outside now, what we call the rejection region, makes up that 5%, where the alpha is 0.05. So we say if it's 5% or less, then it's too unlikely that chance gives us these results. So we reject it. And we conclude that our means are different, or the mean is larger, and so forth. All right, for this problem, our p-value, our actual value, falls within the rejection regions. And because we fall inside that rejection region, we know we're smaller than 5%. We're in that area, our means are different. All right? So we talked about type 1, type 2 errors, right? So type 1 errors is the probability we reject our null hypothesis when we shouldn't. All right? So we reject it when we really shouldn't. Type 2 is when we fail to reject it when we should. All right? Type 1, type 2. Type 1 error rate is what we set. That is our alpha. That's our 0.05. We set that. The type 1 error rate of 0.05 because we say 5% chance of actually making a mistake is tolerable. Right? It's possible, but it's kind of unlikely that we would make that mistake. If we wanted to be more stringent, we just change the type 1 error rate down to, let's say, 0.01. Some of the physics experiments, they set it at 0.001. They don't want to falsely reject it. All right. Type 2, we don't really have as much control over that because the type 2 error rate is based on the true distribution. And we normally don't know that. We don't know that. All right. So how is this all related? I have this figure here. All right. So those watching at home, it is cut off just a little bit. This is the theoretical null distribution and the non-null distribution. So what does that mean? There's a cursor here. All right, so this is the null distribution. That's based on our null hypothesis. This is saying if our means are equal, if our data comes from the same population, this is the distribution of our test statistic. We set our alpha level at 0.05. That means we have 5% in this tail. All right. Now what we've done is basically you're going to learn about a one-tail test, two-tail test. All right. This is basically a one-tail test to kind of simplify and illustrate the relationships between alpha and beta and type 1, type 2 errors. All right. So in this case, we have 5% in this tail. If we get a test statistic, so test statistic is this x-axis. If we get a test statistic that equals or exceeds that value, we're in our rejection region. We're in that area where we're going to reject it. All right? And we set that limit. It's possible that we falsely rejected it. But this is type 1 error. It's the area underneath that null distribution. Beta, it's at the same level, but our area under the curve now refers to this theoretical non-null value. This would be basically the actual distribution that we have. This corresponds to the alternative hypothesis if our alternative hypothesis is in fact correct. All right. but that's our relationship. So the alpha corresponds to the null distribution. The beta corresponds to our actual distribution, the true distribution, which could be our alternate hypothesis. If we want to increase or decrease our type 1 error, we move this line over to make the area much smaller. But what happens to beta? What happens to beta? This line, which is our cutoff point, if we move it to the right to decrease the alpha, what happens to beta? It increases. All right? So if we are concerned about making a type 1 error, we can reduce our chances, but the cost is an increase in a type 2 error of failing to reject it when we should. All right? If we are more concerned about failing to reject it, so the beta, and we decrease the beta, what happens to alpha? It increases. All right? It increases. So our p-value actually corresponds to this null distribution curve. That's what our p-value refers to. All right? So here's our relationship. Type 1 is alpha, type 2 is beta. As alpha increases, beta decreases. As alpha increases, beta decreases. As alpha decreases, beta increases. All right, so they're inversely related. All right. And it happens because of our curve here. So this is what we're looking at. Those curves, we've got our actual null hypothesis, and we have our null distribution, and then we have our actual. And that's we're looking at the area under the curves. All right, so by convention, we try to choose an alpha that minimizes both types of error. All right, and the powers that be have decided that 0.05 does that. All right, so I had a question. So where are the data files for the exam? I can only find question 6 because there's only one data file, and that is question 6. Should be. All right. So we have alpha. We set it. Can we find beta? Yeah, we could. We could definitely find beta. All right. But we have to know that alternate hypothesis distribution because that is the area under the curve that we're interested in. That's what gives us our beta. All right. So we could do it. I have compare a normal 25.2 to a normal 28.2. All right. And we can kind of demonstrate that, and we can actually calculate those things. So, if we were interested, we would draw our null distribution. This is a normal curve. We're centered at 25. All right, that's our null distribution. And then we have a second, the actual, that might be at 28. Say that's 28. All right. So we can figure out what level, what value gives us this area where this is alpha equals 0.05. And then whatever that value is, we look for that area under the curve. And we just use the normal tables or P norm in R. All right, so we could do it if we knew our actual alternate hypothesis. All right, so that's kind of what we're doing. Those are all the terms, the terminology. All right, now let's get to our p-values and talk about our cutoffs and rounding and stuff. All right, so p-values are the probability of getting data as extreme or more extreme by chance alone if our null hypothesis is true. And that's our full definition. All right? It's not just probability of getting data as extreme or more extreme, all right? Because we have that second part that says assuming that our null hypothesis is true. All right? That's the emphasis. All right? That's the emphasis. And it matters how we state it. And this kind of gets us into a statistical hypothesis and a biological hypothesis. all right? Because what we're going to have is we're going to have our biological question, all right? And we could formulate a biological hypothesis, but we don't normally test that with p-values. What we do is convert that biological question to a statistical hypothesis, to a statistical question. And our p-values correspond to that statistical question. All right? What we try to do is make sure they match up so that if we reject our statistical hypothesis, then we also reject our biological question. All right? So we can say those wing lengths of roaches. All right? We can set up a biological question that says, are the wing lengths different in the building? Or does building affect wing lengths in these roaches? That's a biological question. Our statistical question then goes back to the means. Mean of one is equal to the mean of the other, or the difference of the mean is equal to 0. All right? Now, our convention, as I said, is to set alpha at 0.05, which means if we get a p-value that's less than or equal to 0.05, then we reject our null hypothesis. All right? We would say it's statistically significant. Our groups are significantly different. All right? And all of this significance is in the statistical sense, the mathematical sense. All right? Might not be biologically meaningful at all. All right? Getting an increase, a statistically significant increase in mortality. That sounds scary until you realize that we're talking about a chance of dying from 0.1 going up to 0.2. Man, is that biologically meaningful? Probably not. Probably not. All right? So don't get caught up on the significant. That significance is only in the statistical sense, not necessarily biological sense. All right? So note that we will reject our null hypothesis. We can do that. We can say, without a doubt, that it is statistically unlikely that we would get data as extreme or more extreme than this if our null hypothesis is true. We might be wrong. It might be a type 1 error, but we can say that. All right? What we can't say is that we proved our null hypothesis. So if we get a p-value that's greater than 0.05, it's not we proved it. It's just that we failed to reject it. All right? We failed to reject it. Now, how we phrase it, it's not significantly different. Again, significantly in the statistical sense. Also, we can say it's consistent with our null hypothesis. That's different than saying we proved it. It's just saying our data are consistent with our null hypothesis of the means being equal. All right? So in the text, you could use these different terms. We failed to reject. Don't ever say we proved it. All right? You could say that the means are equal. All right? Again, we didn't prove it, but it appears like the means are equal. All right. Distribution of sample means. This gets to our sample sizes. All right? This gets to our sample sizes and why a lot of our statistics work. All right? So if a population is normally distributed and it has a population mean of mu and sigma, here it is, then the mean of our samples of size n will be normally distributed. Doesn't matter what our sample size is, but the collection of all of our means are going to be normally distributed. Doesn't matter what the underlying distribution is. The mean of our samples will be normally distributed. And that's why we work with means, because of this very useful property. We do mean wing lengths. Yeah, the wing lengths may be skewed, but if we repeated it and get a mean every day, get a different mean, the collection of all of those means would be normally distributed. Now, as our sample size increases now the means of the sample size, or the means of our samples, will begin to approach normality. So we say it doesn't really matter, but here's an example. So we're drawing from a chi-square distribution. Our chi-square distribution is skewed. All right, we're skewed right, leaning left. All right, we'll see some of that. And what I've done is generated random samples. I don't know, probably 1,000 or so, or 10,000 samples, and made a histogram. All right. If I had a sample size of 5, if I collected 5 roaches and did their wing lengths, all right, the wing lengths themselves might be chi-square distributed. But as we start to go from measuring 5 roaches to 15 roaches to 50 roaches, look what happens to our histogram. It shifts and now starts to get more and more like a normal distribution. So sample sizes can matter in the sense that the larger the sample size, the more likely we are to follow a normal distribution. And when our sample means follow a normal distribution, then we can utilize statistical tests that make that assumption, that rely on that property. This is the basis of a parametric test. A parametric test relies on normality. What about the variance? The variance is a little bit different. All right, so the sample means are going to approximate our population means. All right, they're going to converge. The standard deviations and the variances don't quite follow that. All right, so if we take repeated samples, yes, the collection of all of our standard deviations will start to approximate the true value, but we can't take like an average of the standard deviation to represent our population. All right. When we do that, which we'll see, and this is kind of a mathematical way to show all of this stuff. What we end up getting is that we're interested in the standard deviation of all of that collection of means. So going back here, we're interested in the standard deviation of this histogram. That's what we're interested in. And since we're graphing the means, we're kind of doing something that's a little bit different. So this is what we calculate, the standard deviation of the mean. But what that value is also, or another name for this value, it's the standard error. The standard error. So you take the standard deviation of your sample, you divide it by the square root of our sample size, and that gives us the standard deviation of the mean. So we get a sample, we have a sample mean, sample variance, sample standard deviation S, and then the standard deviation of our mean is this S divided by the square root of our N. All right. Now, the reason we do that is because our sample standard deviation is going to be sensitive to our sample sizes. All right. So if you're comparing different samples, you don't really want to utilize standard deviations because it's possible that your samples have a different sample size. You may have 10 roaches in one sample, but 25 roaches in another sample. That's going to give you a different standard deviations, possibly due to differences in sample size. But if we standardize it, if we normalize it by dividing by the square root of n, we calculate a standard error, and that eliminates the effect of our sample sizes. All right, and that's kind of important because, again, as our averages, as we do more and more samples, our averages converge. This. Our averages converge, and that's what this is saying. And so blue is taking a sample size of 5. Where's my cursor again? There it is. Blue is a sample size of 5. You can see our average does converge, but if our sample size increases, now we get a very peaked distribution. Standard deviation gets narrower. So our standard deviation values will also will cluster around the true value. All right, so I have code for all of our graphs here. If you want to know this, I'm not going to ask you about that information. That's kind of background information. Getting to our standard errors, because that's going to be what we'll use to compare groups. There it is. Standard error of the mean is also called the standard deviation of the mean. Right. If we have an observation of a sample, then we'll use standard deviation to represent it, because this describes variation within the data. But, and that's just observation, if we have any hope of making some sort of statistical comparison, then we need to use standard error. All right? That's our distinction. So if we just make an observation, if we just measured something and we're reporting on this sample, this is the mean, this is the standard deviation, that's fine. You'll see it in morphological reports, species descriptions. You'll see mean and standard deviation. It's just observation. But if we are going to compare them to other values, to other samples, and say if they're different or not different, we need to use a standard error. So both of them describe variation within the data, but the standard error is going to talk about the variation of the mean of the data, because it's going to recognize that if we take a repeated sample, we can get a different mean. So the standard error describes that amount of variation, how our means will change if we take a new sample. Typically, you will report the standard error in a scientific paper or on a poster. All right, don't report the standard deviation unless it's a morphological study. Report the standard error. How do we do it? Well, you can calculate the standard deviation, ST, and then divide by the square root of our sample size, right? Or, here's a function that I made, all right? So, I'm going to talk about this function and how R works with functions. So what you're going to do, go ahead and open up your R Markdown, or R Studio. And you can make this, you can make a new one, because what we're going to do is learn about confidence intervals as well in this. So, make a new Markdown document. All right. All right, so here's my R Markdown. Make sure I get it here. I called mine SC and CIs, standard error confidence. In order to calculate a confidence interval, we need to know the standard error. That's why. All right, so what we're going to do is just demonstration. Function. I don't know if we need the libraries. All right, we're going to start with data generation. All right, so let's just go ahead, set the seed to whatever you want. All right, just any number that you want. We don't need to have the same number. We're just going to do this to kind of demonstrate that our functions work. All right. All right, so I'm going to set the seed, and then I'm going to generate a data set. So I'm going to do something like, I guess I'll do a randomized chi-square since we've done that before. And I'm going to do 20 sample size, and I'm going to do df is 4. Okay. And I'm going to run the script. Whoops. Before we do that, we have to save it. So I'll just say rdat, I don't know, randomized data, something like that. And then I'm going to rerun that chunk. So that way rdat is in memory. All right. So standard errors. All right. So to calculate a standard error by hand, we just followed our equation. All right. And that was standard deviation of our rdat. All right. Standard deviation divided by the square root of SQRT, the length of rdat. All right. Now we didn't have missing data in it, but if we did have missing data, we would go through that selection process. Again, where we would only calculate the length of the non-missing data. All right. All right, so just kind of getting in, the actual formula and our markdown so we have it. All right, and then I'm going to run it and see what I get. All right, so I get that's my standard error. Now, 2 times this amount can approximate a 95% confidence. It's an approximation. In this case, it's a very poor approximation because my underlying data are not normally distributed. And we can check that, all right? How do we check that? What can we do to see if our data are normally distributed? What's that? What would we do? Do what? Yeah, we can do a QQ plot. What do I have to load first? Does QQ plot run right now? No, what do we have to do? Yeah, load the car library first. That's kind of why I put the libraries up here. If we needed the car library, we'd load it in there. All right, and then we can do a QQ plot, see if our data is normally distributed. And you'll see we're not, all right? We're skewed. But we do have a standard error associated with this. We can calculate it, all right? Now, I give you a function to calculate the standard error. And that function is STERR, right? Right? STERR. So, so we can use the function STERR to calculate it in one step. So I would just do STERR of RDAT. Now when I run it, you're going to see that I get an error. Because STERR is not found. We didn't define it yet. It's a function, but it's not built into R. So what we have to do is get that function into R. So up in my functions, I'm going to type it out. So I don't think that na.rm equals t even works, believe it or not. I'm going to take that out. We don't necessarily need it. All right, so what we've done is I created an object called STERR, for standard error, right? I've got my arrow, because I'm going to create an object, and that's what I want it to be called. The object that I'm creating is a function. So function and then x. X is the option that we pass to it. So if we had like mean of x, the mean was a function. It was called mean. And the option that we had was x in there. We gave it a vector, all right? So same type of thing. We're creating a function, and we have to give it something, all right? After that, now I have the curly braces, all right? The curly braces is going to say inside of these braces, this is what we're going to run, and we're going to run it line by line. All right, so the first thing that we're going to do is set up an if statement. All right? All right, believe it or not, this is an if-else statement. It's going to run a check. All right? Oops. Actually, we do need na.rm equals t, because that's what it's doing. So the default is na.rm equals t, which says remove the missing data. I don't know when you would ever not use it. All right? And I say that because if you have missing data and you didn't have it, when it runs the standard deviation, the SD function, it's just going to return NA, and that means your standard error function is going to return NA. So what we're doing is we look at this. If na.rm is true, then what it's going to do is this. It's going to run this na.omit function on whatever object we pass to it. What na.omit will do is take the object and strip out all of the missing data. If you think about the length function that we did, all right, that length function had the brackets, and we selected out all of the NAs. This does the same thing, but it does it all in one step. All right. Now this is going to work on a vector just fine. This also works on a data set, on a data frame, but I'm going to caution you that this na.omit will remove all rows that have any NAs in any of the columns. So if you have, if you did, a 10-column data set, right, 10 different measurements, and you have one measurement missing for, let's say, dissolved oxygen in one of the lakes that maybe you're measuring, in a limnology class, you lose that entire row, which means it's not going to be available for all the other measures. That's not usually what you want to do. So na.omit's really great for vectors. All right, so what we do is strip out all of the missing data first, and then once we have the missing data out, we are going to run the same thing that we just did. Standard deviation of our vector divided by square root of the length of x. Don't have to worry about missing data. We already stripped it out. Now, R does all of this stuff. I kept using XXX. When we actually give it our data name, so in my case, RDAT gets replaced. It replaces all of these x's. That's what the function is going to do. And then the end of this curly brace says, okay, the function's over. Now what we have to do in order to make this accessible is we have to run it. So I'm going to run the chunk, and what you see now is that I have a function that we've now created, and it's available in memory. Once we have that, now I can scroll down to my sterr and run it. And I get the exact same answer. Why do this? Why do this? I'll show you. Just to demonstrate. I'm going to import a data set for you. This one, let's see here, all data. Let me find something here. Fish. I think fish line. All right, fish line. This is a data set that we'll work with. This is part of our analysis of variance stuff. All right, so it's posted. All right, so I've read in fish length. It's accessible. All right, and one of the things that we want to do is look at our fish length. Oftentimes, one of the first things we want to do is get the mean. So in this, I'm just going to make a plot of fish length. Let me look. It's lake and length, I think. Yep. We're going to make a plot of length as a function of lake. Data is fish length. All right. So I just kind of make a figure. There it is. All right, so we've got five different lakes. All right, this is a box spot. We'll learn about them. All right, we want to report the means in a page. We want to know the actual means. Maybe we also want to know the standard errors. As we're going to learn when we get to the ANOVA, I can do this using a function called aggregate. All right, where I want the aggregate of length based on each lake. Data is fish length, and the function that I want to run is the mean. All right, and what this does will give me the mean of each of the lakes. Very easy. If we did this in Excel, we have to go highlight the individual columns that correspond to the different lakes. If we broke it apart by lakes, or if we have two columns like you need to do in here, you kind of have to manually select the different lakes to go get this. In R, the aggregate function will do that for us. It takes our data, aggregates it by lake, and then performs a function on it. That's our function. Now, if we're going to make our own figure, we need the means. We also need the measure of dispersion. Standard deviation really isn't good because we're going to be comparing these means, so we should report the standard errors. There is no built-in function for standard error. We can't use fun equals SD over length. It won't work. This needs a function, which is why we created STERR, standard error. So now we have the standard errors. Now, R, nothing against the box and whiskers plots, but if I'm making a publication quality figure, I'm going to probably try to do it in Excel. There's some exceptions. There's some things Excel just really can't do, and I'm forced to do it by hand in R. All right? And the values that I need to do it by hand means standard error. So now you have the function. We just have to remember with that function, put it right at the top, make a section called functions, have that function run it, and now STERR becomes available, and you can use it whenever you want. All right? We will be using this. Questions? So standard errors, we did that. I do have one other example here. So I have run the following, and this kind of does exactly what we did. Now I did the arc-I squared because we're going to be doing 95% confidence interval, and specifically a bootstrapped confidence interval to generate those intervals when our data are not symmetric. But that's up here. You can run it on your own time and see that, yeah, this function works just great. Just great. All right, so how do we report our data then? So the mean, we need to report central tendency. We need to report measure of dispersion. All right, that's what we have to do. Typically, we're going to report the mean, and if we report the mean, then we should be reporting either the standard deviation, the standard error, or the standard error. If it's just morphological, if it is just description, no statistical analysis, standard deviation is fine. If we're doing any sort of statistical analysis on those means, we need to report the standard error. All right? So here are the two ways, typical usages of reporting. We would report the mean plus and minus our standard deviation, or the mean plus and minus the standard error. All right? So again, this is how you report it. So you can report acetabulum is 7.1 plus or minus 3.25 millimeters in diameter. Or you report the mean and then put SD equals 3.25 millimeters in parentheses. Both ways are appropriate. All right? Standard error gets reported in much the exact same way. All right? In this case, I could have done, in this case, I used the mean plus or minus standard error. So I did, exhibited an average IVU of 45 plus or minus 2.2 SE. Now, note the difference. I have our units in the text. I have the units in the text. So that means when I report it, I specify SE to let the reader know that I'm reporting the standard error. Up here, I did the mean, and I included the units with the mean, and then in parentheses, I reported the standard deviation. And again, I'm reporting SD to let the reader know that we're reporting the standard deviation and not the standard error. If I wanted to report standard error like this, I would do that. It said the most recent batch of beer exhibited an average of 45 IBUs, parentheses, SE equals 2.2 IBUs. What is IBUs? Anybody? Branching out, where this is like a liberal arts school. Learning more about, not all about math. International bittering units. It's kind of how much bitterness is isn't a beer. So, but anyways, that's how we report it. Now, rounding is important. Note our standard deviation and standard error in this case. We always go to one more digit than what we rounded our means. So in the first one, we rounded to the tenths place, and that means our standard deviation went to the hundredths. In this second example, we rounded to a whole number. That meant our standard error goes to one more digit. All right? There's one other bit about that the averages and the rounding bit, but I think what we'll do is we'll pick that up at another time. All right? So, review this. Standard errors. It's really not going to be a whole lot of homework until we get to the confidence intervals. This is all leading up to confidence intervals and then how confidence intervals relate to statistical tests and p-values. All right. All right, so I will double check the exam, but I am almost 100% positive that there is only one data file for that exam, and it is for question 6. All other data files or any other data is included as either something that you'll have to create a vector or convert a table to a vector. And really, if you think about it, it's just been probability. I'll double check. I'll be back here. Maybe a little, hopefully by 2. Maybe I'll be a little bit, possibly a little bit late, but I'll be here until 4 in the lab or in my office in case you have problems knitting your document. All right? All right, and if you are doing it at home and we're having errors, and we can't get it resolved, you can get a screenshot. Then what we may have to do is set up like a Google Collaborate or Google Meet or something like that where you share your screen, and then I can see what you're doing and we can kind of set from there. We'll see. All right, we're done.